Let's look now at the second right-hand rule. So again, we're going to use this second right-hand rule to figure out something related to magnetic fields. So we will use this to find the magnetic field caused by current carrying wires. So let's say that we have a straight long wire and it carries a current I. Then the magnetic field given by the straight current I is going to form circles around this current, and the magnitude of this is going to be given by mu naught I over 2 pi r. Now the equation doesn't tell us really a lot about the direction of the magnetic field. This is just the magnitude of it, so I guess I can write it as a magnitude. And the direction is given by the right-hand rule. So you place your thumb in the direction of the current and pretend like you're holding on to the current. So you have the current in your hand, the wire in your hand, and then to hold it, you have to close your hand, right? So the direction that your fingers are going in is the direction of the magnetic field. So you can rotate your hand all around the current carrying wire. So depending on the area of interest of where you're looking for the magnetic field, it can either be into the page or out of the page, or maybe to the right in front of the wire, to the left behind the wire. Okay, so thumb is in the direction of the wire, so it's pointed along the current, and the magnetic field rotates around. Now, the shape of the wire can change, so you can have a loop of wire, and the loop of wire looks like this. It could have several different turns, and let's say that the current is going in this direction. One thing you have to remember here is that the magnetic field is concentrated in the center, or within that loop. The magnetic field outside the loop is negligible. So always make sure that you're only looking for the magnetic field inside that loop. The equation for the magnetic field, for the magnitude, is mu naught I divided by 2r. So it's very similar to the equation that I wrote above, but this one doesn't have the pi in it. So this is the current. If we want to find the magnetic field, we have to place our thumb in the direction of the current. So it goes with your thumb in the direction of that arrow. And you have to make sure that your fingers, your bent fingers, are inside the loop, so that when you rotate your hand, your thumb goes around your hand. Okay, so place your thumb in the direction of the current with your hand inside the loop, not outside, but inside the loop. So the thumb will rotate around your fingers, your bent fingers. So when we do that, the magnetic field is in the direction of the fingers inside the loop, and that will be coming out of the page. A third type of configuration would be a solenoid. So I guess I should write here straight wire, this is a loop of wire, and then we have a solenoid. Okay. One more thing that I want to mention about a loop of wire, which is also relevant to the solenoid, is that a loop of wire doesn't have to just have one turn. So if it has n number of turns, then the magnetic field is n mu naught I over 2r. For the solenoid, it looks kind of like a slinky or like a spring. And again, something to pay attention to is the fact that the magnetic field is only inside the solenoid. It's negligible outside of it. And the equation for the magnetic field in a solenoid is going to be mu naught lowercase n times I. The lowercase n is the number of turns of the solenoid divided by the length of the solenoid. Not the length of the wire, but the actual length of the solenoid. Okay? It is kind of hard to tell if, this direction of the current is down in front of the solenoid or down behind the solenoid. So then we're going to cut a cross section of the solenoid. We're going to cut it in half, and it will look kind of like this. So let's say that the current is coming out at the top, in at the bottom, out at the top, in at the bottom. So it rotates out, in, like that. Okay? So now we will place our thumb in the direction of the current. So I guess on the bottom, the current is going into the page, and we have to make sure that our fingers are inside the solenoid. So that means that the magnetic field is going to go to the right, inside the solenoid. Okay? You can also look at it at the top half of the solenoid where the current is coming out. So you place your thumb so it comes out of the page, and then the bent fingers inside the solenoid will also go to the right. Okay? So things to remember are that the current is your thumb, and the magnetic field is your fingers, your bent fingers in all of these cases. And also that for loop of wire and for a solenoid, the magnetic field is only inside the loop or solenoid. All right, that's it.